Ahmed.
Okay, yeah, thank you very much. Thanks for the invitation. It's very nice to be here. So what I'm going to be talking about today is all joint work with Gabriel Corrigan and Dan Sims. And these people are actually both undergraduates. So this was an undergraduate summer research project that we did this summer, which I think we all had a lot of fun with. And I would just mention, I mean, these two people are both currently applying for PhD positions, many of them within continental Europe. So if there's anyone watching who comes across one of these names, these are both very good people. So you should hire these people. Anyway, so I'm going to be talking about tropical maps and log maps in that order. So this will be section 1, and this will be section 2, and then I'll explain the result. So let me start off where we're all a bit more comfortable, including myself. I should put a little warning here. So what I'm going to do is I'm about to define some notion of tropical map. Okay, and as usual in this story, I'm going to have to set up some rules of the game. And the warning is that these rules may be slightly different from the rules you see, okay, in other contexts. My rules are set up in such a way that they play well with this theory of log stable maps, which I will come to. Okay, so you just have to trust me that these are somehow the right rules when we're in this situation. On the other hand, I think that the differences between the different games, let's say, are not that important. So I'm fairly confident that whatever version of tropical maps you have in mind, the main theorem will also apply there. But you can feel free to ask me questions about that. Okay, so I mean, I think probably everyone here knows what a tropical curve is, but anyway, let's make sure we're on the same page. So for me, this will be a metrized graph. So I have some finite graph, something like this, and then I have positive real edge lengths associated to the edges. So for example, maybe this has length 1, maybe this has length 2/3, maybe this has length √2. Okay, so just an abstract tropical curve. It doesn't come at the moment. It doesn't come with any embedding into a vector space. Okay, and now I'm going to think about maps from this tropical curve. So I should tell you what the target of these maps are going to be. And so for today, the target is going to be the positive orthant. Okay, so Rn, I'll write it this way. This is just notation for Rn really big or equals 0. And I'm viewing this as a sort of rational polyhedral cone. Okay, so in particular, I'm sort of remembering the fact that there's a lattice sitting inside it. Okay, so I'm viewing this as the if you like, it's the cone that defines affine space as a Freud correct. Okay, so this is going to be my source. This is maybe we'll put it as gamma, and this is going to be my target. And then I'm going to study maps. Okay, let's say F from my tropical curve to this positive orthant, and I want these to have integral slope vectors. Okay, so I will explain what that means via some examples. Integral slope vectors, or we could also call these expansion factors. Just weighing me down. Okay, so let's see, where should I go? I should start it. Sorry about that. Let's try this way. This is not so bad. So here are a few examples. Okay. Can somebody online tell me, is this color visible? It's okay? Okay, great.
Yes.
Oh dear. Well, okay, let's leave that there for now. Okay, so let me give you a few examples of these things. So I'm going to start by, so the first two examples will just have n equals 1. Okay, so here's my R positive. And since I have the orange chalk in my hand, let's draw another one for later. And then in the first example, it's quite simple. So my source graph just looks like this. Okay, and it has some edges. Sorry, it has some edge lengths rather. So I'm not going to say what these are right now. They could be anything, any positive real numbers. And then this is sort of mapping down. Okay, and I should tell you, so there's some metric here and there's some metric here, which is the standard metric. And I should just tell you how this map interacts with the metric. So what I'm going to ask is that it sort of expands things. Basically, it's metric preserving here, but here it expands things by 2. Okay, so what that means is when I look at the images of these vertices, so this sort of length here is the same as the length upstairs because of the 1. So this is E1, this length. Whereas down here, the length is sort of grown because this 2 told me to expand the map by 2. Okay. Okay. So here's another example. Also fairly simple. So almost the same. I mean, the graph is the same. So I still have E1 and E2. But now I'm mapping it in this way. So I've decided to map both of these vertices down to the origin. So you can see what I meant when I said I'm thinking of this as a cone. You can see that somehow the faces of this cone, in this case, the origin and the whole thing, are playing some important, special role here. Okay, and I should tell you again what these expansion factors are. So I'm going to take the same ones as before, but now because of the way I set things up, the picture is quite different. And so now if we think about the distances in the target, so if we think about this distance here, well, we can either go from this vertex, we can sort of start here and end up at this internal vertex, and that would tell us that this is E1. Okay, or we could start here and go here, and that would tell us that this is 2 times E2. Okay, so either of these formulae will give us a formula for this length. Okay, let's do one higher dimensional example. So, so this is R2. Okay, my curve is going to look something like this. So let's see. So this is still really a map, not an embedded curve, but I'm going to draw it as an embedded curve. So it has 3 vertices, they're mapping like this. And again, so let's say the length is E1, and the length is E1, and the length is E2. And now I have slope vectors, right? So I have to tell you how much it expands the metric in each of the 2 directions. And so here I've taken sort of 1, 1 here, which you can sort of see in this picture, and 0, 1. Okay. And notice in this case, right, that if I sort of pair off here and measure this height, then again, this can ultimately be described as E1 or E2. So these 2 lengths have to be the same, which is not really saying anything very dramatic. Okay, I mean these are lattice lengths. Okay, so it's just saying that this is a right angle triangle. Okay, are there questions? So this is my setup. Perhaps the experts in the audience will have, might be slightly uncomfortable with what I've drawn here. So you'll notice there's no balancing condition in this story, okay? And that's by design. Basically, the reason for that is that because later what's going to happen is we're going to look at logarithmic maps to arbitrary pairs as opposed to toric varieties. And since I'm working relative to arbitrary pairs, I can essentially decide that the components of my divisor are independent in the Picard group, which basically means I'm allowed to choose my sort of, intersection numbers with respect to the different divisors independently. Okay, so that's sort of morally speaking why we're not seeing a balancing condition here. But I will try to remember to mention this again when I come back to discuss logarithmic maps. Okay, questions? Yeah.
Just to make sure, is 0 allowed as a dilation factor?
Yes, yes.
And it's necessary for this example that you had in the first place, right? The one above, the gamma. Because there we have 2 different vertices, and one has length 1. And
but this one here, yes, right. Well, I guess also, let's think about it. So this is probably okay, right? Because I suppose I could have expansion factor 2 here and 3 here.
Oh, okay, that's it.
Okay. Yeah, unless I misunderstood what you were saying, I think it would be okay. But yes, you can have edges with 0 expansion factor. They generally don't play a super important role in this theory of tropical maps, but they certainly, I mean, it's important that you allow them, but they don't really complicate the theory that much. Yeah, good question. Other questions? Okay, so this is the game we're playing. So let's try to build a bit of a theory here. So I'm going to introduce this notion of what's called a tropical type. This is also sometimes called a combinatorial type. And so basically what a tropical type is you start with some tropical map, and you just forget the data of the edge lengths, okay? So you forget the edge lengths, but you remember everything else, okay? And so if you do this, what you're left with is essentially discrete data, right? So the edge lengths are not really discrete because they can take any real value. But what you're left with is essentially discrete. So let's just spell out what it is, okay, just once and for all. So you have the source graph, right? But now it doesn't have any metric, right? We forgot it. So you have the source graph, and then for each of the edges, okay, so for every edge in the source graph, you have a slope vector, okay, which tells you the slope, and actually, really it should be for every oriented edge, okay? So you should choose an orientation, and if you take, okay, so little arrows on top of everything, and if you take the reverse orientation, then the slope vector should be reversed, okay? So there's some slope vector here, and then so this probably is familiar to people who think about tropical mass affine spaces, okay? But there's a bit of extra data here, which is a little bit more sort of specific to this situation, which is that for every vertex of the source graph, we associate some face, okay, of Rn positive. So like in this picture over here, right, I really wanted to insist that this vertex here was mapping to the origin, okay? And I'm sort of allowed to do that because its origin is a face, okay? And we'll see why. The reason for this is, again, because it reflects the sort of geometry of these null maps, okay? So we'll see that in a little bit. So there's this assignment, and similarly, there's this assignment for the edges. Okay. So, but in any case, some discrete amounts of data, and you know, if we fix various things at the beginning, then we can sort of enumerate these. Okay, so associated to this, so if I give you a tropical type, we get something called the tropical moduli space. Okay. Okay, and what this is it's just the it's just the moduli space which parameterizes edge lengths. In other words, metrizations of gamma, which are compatible with all this discrete data, which I put in. Okay, so this parameterizes. So in other words, I forgot the edge lengths. Okay, I've gone down to here. Now I want to put them back in, and I want to know how many ways I can put them back in. Okay, so parameterizes. Oops. Yeah, so metric enhancements. I guess that's the best way to say it. So metric enhancements of gamma, which are sort of compatible with all of this data. So let me explain. I'll explain what I mean by this. Okay. So let's go back to these three examples on the left. Okay, so in each case, I'm going to tell you what the tropical moduli space is. So in the first example, right, so I'm basically allowed to choose these lengths E1 and E2, and I can essentially choose them independently as I like, right? So E1 can be as long as I like, E2 can be as long as I like. And so in the first case, the moduli space is just R2 positive with parameters E1 and E2. But the second case is a bit different, right? So notice the source graph is exactly the same. Okay, so if I ignore the map, I'm allowed to choose E1 and E2, so it seems as if I have R2 positive. But of course, you notice that in order for this map to be sensible, I have a relation here, right? E1 and E2 are dependent because I'm imposing that this map has the same, well, has these dilation factors here. Okay, so E1 is equal to 2E2 here. So let me write that again. So here, so in other words, because of the way I set things up, because of the shape of the graph, these two edges can't be chosen independently. Once I choose one, I get the other. Okay, and so here, so for the second example, the tropical moduli spaces are positive with well, it doesn't really matter, but let's say coordinate E2. I prefer E2 because if I'm thinking of the integral structure, then sort of E2 determines E1, but not vice versa. But anyway, if you think about it just as the real numbers, then take either E1 or E2 here. It's sort of fine. And again, for the final example, it's basically the same. So I mean, you'll notice the graph is actually the same in all three of these examples, right? And again, for the final example, because I'm essentially insisting that both of these two vertices are lying along the x-axis, right? Then if I just look at this from the side, it basically looks exactly the same as this picture here. Okay, so again, I get R positive. Okay, so not super interesting. Yeah. Are there questions about this? So notice, okay, so
one question.
yeah.
how does this relate to the moduli space of the tropical curves of the, say I fix the genus and like the combinatorial type? How does this relate?
Yeah, very good question. Okay, so I can do that. Let's see. Let me give. Okay, I'm gonna answer your question on this one. Let me say one thing first. So all of these you'll notice, right? These are always rational polyhedral cones. Okay. So let's come to your question. So what I can do, so as you say, let's for example, let's fix the genus of the graph, and I guess there's another picture which I guess is implicit here, which, well, we could just fix the genus of the graph, maybe. Okay, we could also have some markings if we wanted to, but that's fine. Then there's this space MG trop, okay, and this is a cone complex or a cone stack, right, which parameterizes abstract graphs without any abstract complex, without some map, okay. So this is a, I'm gonna say this is a cone complex, but I mean really it's a stack, but that's okay. But anyway, it's something that looks like the Fan and toric variety. It's obtained by taking a bunch of rational polyhedral cones and gluing them together along faces. Okay. In this world that we're in now, so now I'm looking at tropical maps. So what I can do is I can look at something I'm going to do TG are positive. So what this is this is the space of tropical maps to R in positive. And this is again a cone complex. And the cones, okay, so this is a cone complex, and the cones are going to be indexed by these tropical types. Okay, so the cones indexed by tropical types. So so really, I mean, I've committed sort of maybe a sin here. So if I specify a tropical type, I told you there's an associated tropical modular space, and that was just a single cone. So really, what that is it's a single cone inside this cone complex, and they're glued together in various ways because there's a well-defined notion of specializing tropical types. So this cone complex maps to this cone complex because you can take the map and just forget the map and just remember the source code. Okay, and this is a morphism of cone complexes. And there's various things you can ask about this. So, for example, one question you can ask, which is sort of close to my heart, is this the analog of what we call a flat morphism in algebraic geometry? There's a notion of this for cone complexes, and the answer turns out to be no. And anyway, so this has been studied actually in a lot of detail. Yeah, thank you. Thank you. Other questions? Okay, so so far we haven't actually, so I keep saying this is a cone complex, we haven't actually seen many interesting cones appearing yet, right? They've all basically just been orphans, okay? But it turns out this doesn't always have to happen. So let me show you an example of an interesting rational polyhedral cone. So I'm going to define another tropical type. Here's what I'm going to do. I'm going to take just map into R positive again. And my graph is going to look like this. So I have 4 edges, so I have 4 lengths associated to them. Okay, and I'm just going to take all of the expansion. So the slope vectors are just numbers here, and I'm just going to take all of them to be 1 in this case. Okay. So now what you see is that okay, I'm allowed to choose these 4 things independently, but there's one condition, right? Which is that if I measure, so these 2 vertices are allowed to map to different points down here because I can kind of move this around. But this final vertex maps somewhere here, and if I measure this length, this way round it's E1 plus E2, and this way round it's E3 plus E4. Okay, and so what you find is that the corresponding moduli space is called sigma. It's the set where E1, where this equation is satisfied. Okay, so it's this set living inside R4 positive. And I'll let you convince yourself of this, that this is actually sort of as a cone, and this is isomorphic to the basically the quadratic. Right? So the thing that I got my dotted lines wrong. So it's the cone over the square in 3 dimensions. Okay. So this is the rational polyhedral cone whose associated toric variety is the what is this called? The threefold ordinary double point. Okay. So this is all just a way of saying that. So we start with one of these tropical types, which is this discrete amount of data, we produce some tropical moduli space, which is a rational polyhedral cone, and that determines an affine toric variety. And that affine toric variety may be singular. And this is going to come up again in this talk. Are there questions? Okay, so let me tell you why I care about these things, why I care about these terms. Great. I've been observing the previous things. So I said that these tropical maps are supposed to be modeling something in algebraic geometry, and these are these things called logarithmic maps. So let me sort of introduce those. Okay.
Good job, yeah.
Thank you. So I'll just briefly recall the theory of stable maps. Without going into too many details, I'm going to focus on some peculiar aspects, perhaps. So you fix some smooth projective variety, okay, and out of this, you can construct a moduli space, which I'm just going to write as mx, or okay, maybe I'll write mx. That's a little bit closer to the usual notation. So what this is it's basically a space parameterizing. Well, it's a space parameterizing parameterized curves in X. Okay, so it maps from an abstract curve into X with various conditions and decorations. So what are those? So this curve C is an at worst nodal. Okay, and then I also decorate it with some number of points in the smooth locus. This will allow me to impose incidence conditions on these curves. And then I have this condition that the stability condition, which is that F has finitely many automorphisms. Okay, and this condition ensures that this space is separated and proper, and it's something that we can do intersection theory on. Okay, or is it? So here's a theorem. So this is due to Vakil. Although, yeah, it sort of builds on earlier work of Neff, but I think really this theorem is due to Vakil. So this is this is the space, this is the moduli space of stable maps. Okay, and this is something that leads to the central object of Gromov-Witten theory. These spaces exhibit arbitrary singularities. Okay, class of spaces. So what that means precisely is that if you give me any complete local K algebra, I can find one of these spaces and some point on that space whose local ring is isomorphic to that algebra. Okay, so this is often referred to as Murphy's law in algebraic geometry. This is this proverb that if something bad can happen, then it will happen. I guess the slightly less flashy name is Universality. Less or more flashy, depending on your personality. Okay, so it exhibits arbitrary singularities. Okay, so this is pretty bad, right? So in particular, these spaces are not irreducible in general. They have many components with many different dimensions. But it's not all bad, actually. So it turns out that despite this theorem, all of these spaces are what's called virtually smooth. Okay. And so what virtually smooth basically means is, yeah, okay, it's not smooth, but we understand the deformation theory of these objects well enough to work with this thing. Okay, that's basically what this phrase means. So let me be a little bit more precise. So there's this object with a perfect obstruction theory, which again is basically some package which allows you to stand up and say that I understand the deformation theory of these objects, of these things that I'm parameterizing. And what this perfect obstruction theory does is it furnishes this space with all of these things that essentially, it furnishes this space with a bunch of structures which play the role of the structures that would exist if this were a smooth variety. Okay, so there's something called the most important of which is this thing called the vertical fundamental class, which plays the role of the fundamental class of a smooth variety. Okay, so roughly speaking, how this is defined is that the perfect obstruction theory, so at least locally, is expressing this singular space as the vanishing of a section of a vector bundle on a smooth space, but that section just happens to not be transverse, okay, which is why you have all these singularities and excess components. And so what this virtual fundamental class is doing is it's basically taking the Euler class of that vector bundle, which is what provides you with the fundamental class of an actual transverse section. So it's sort of, in other words, it sort of perturbs the section in some sense, but of course in algebraic geometry you're not allowed to do that, so it provides a sort of next best thing. Okay, and so this virtual fundamental class again plays the role of a fundamental class, and in particular you can integrate against it, so you can cap cohomology classes against it, and this is what leads to these things called Gromov-Witz invariants. So these are just intersection numbers against this class. Okay. So anyway, so in other words, things are as bad as they could possibly be, but in some sense, actually, things are not so bad. So we can really work with these things. And it's not just that we have this class; we also have techniques for calculating these invariants. Okay. So some of these I'll just mention. So one of the most important is torus localization, which allows you to exploit symmetries of the moduli space to calculate these invariants. There's also various other things, sort of picked almost at random. There's a bits for Green-Rock theorem and so on, various other things like this. Okay, okay. So this is the story for the stable maps. Let me get onto these log things now. So log stable maps actually, in many ways, although it seems somehow like I'm taking this theory of stable maps and making it more complicated. For a tropical audience, actually, in many ways, this is simpler than the theory of stable maps. So this was in many ways actually inspired by these tropical correspondence theorems of Mikhalkin and Mishin, Zivert, and various other people. So the starting point here is, so instead of starting with X, you now start with a pair. Okay, so I have X and then I have a D. And so X is still going to be smooth. But this D is, this is a simple normal crossings divisor. Okay, so what that means is that its components are smooth and they're intersecting transversely. Okay, so this pair, this is actually the prototypical example. An SNZ pair is sort of prototypical case of a toroidal embedding, which is a very old notion, and it goes back to the earliest book on toroid varieties called toroidal embeddings, right? So toroidal embedding is basically a pair which is locally isomorphic to a toroid variety relative to the toroid boundary, but not necessarily globally. Okay, and this is a special case of a toroid embedding where all of the toroid models are smooth in this case because I'm assuming X is smooth. So there's weakened, and in fact, this whole theory actually works without that assumption. Right? It's just it's locally toroid, but for today we'll stick with the smooth case. Okay. So locally this thing is isomorphic to a toroid variety, so locally there are toroid models. And to any toroidal embedding, I can associate this thing, which we call the tropicalization, we meaning like sort of in this community. I say that because of course there are many other notions of tropicalization, of course, they are related. So for every, okay, let's write this a little bit better. So for every toroidal embedding XP, we associate this tropicalization. Okay, and this is basically playing the role of the fan of the toroidal embedding. There's just one crucial difference, which has come up already, which is that this is an abstract cone complex. Okay, this just comes from the fact that this thing is not globally a toroid variety. Okay, so the way this is constructed is this has local toroid models, and these define rational polyhedral cones. And as you're moving around along X, you pick up all these cones, and you can glue them together along faces. But the point is that these cones don't, the crucial thing is that they don't come embedded in a single ambient vector space. Okay, so this thing has no preferred embedding into a vector space, so it's not a fan. Right? It's a fan in every way except the fact that it's not embedded in a vector space. Okay. But nevertheless, it has many of the same wonderful properties that a fan does. So, for example, two that are very important is we can consider subdivisions of this thing, and these will correspond to birational modifications of the original pair. Okay, in the same way as we do as we have in torque geometry, and also we can consider piecewise linear functions on this thing, and these will correspond to Cartier divisors here that support along the boundary. Okay, so a lot of the toric dictionary kind of carries over to this case, and this turns out to be very helpful when you're trying to think about complicated moduli spaces. We haven't got there yet. So okay, so this is the starting geometry. So I have this pair. It's a toric embedding. We'll come back to that in a minute. But just as in the previous case, I was studying maps into X. Now what I'm going to do is I'm basically going to study maps to this pair. Okay, so what that means is I study maps to X with some specified tangency profiles along these divisors. Okay. Great. Maybe this is going to be worse enough.
Do you allow all kinds of tangency profiles, or?
Yeah, so yeah, I guess I can start saying what I'm going to allow. So for every, so in my setup, I have, that wasn't such a good job. I have so I have my curve, and my curve also kind of has a divisor on it, which are these mark points. Okay, so I'm sort of mapping the pair of my curve together with the points to the pair of X relative to the divisor. And so basically what I do is that for every one of my points, EI, I specify which tangency orders I want it to have to every one of the divisor components DJ. So I sort of have a matrix of tangency orders where the rows are corresponding to the points and the columns are corresponding to the divisors. And I can basically, I can choose that arbitrarily. So that, I mean, the tangency, of course, for every divisor component, if I sum up the tangency orders, it should equal the intersection number of my map with the divisor. But other than that, we can choose it arbitrarily. So if you like, you can think about it as a partition of the as a non-negative partition of the intersection number. Yeah, thank you. Are there other questions? All right, let's see how we're doing. Okay. Okay, so yeah, so let me write that down. So we have this. So okay, yeah. So I guess I just said this. So we have this matrix alpha. Okay, and this is encoding somehow the tangency of f. So this map f to the divisor di at the point pj for all I and j. Okay, and we fix this data at the beginning. Right. Once we fix that data, this gives rise to a modular space. Okay, so we have this modular space. I'm going to write it like this. So log alpha x rel t. And so this is basically parameterizing the same thing. So I'm going to write it like I just said. So I have this somehow this map of pairs, something like this. Okay, and why don't we just write down what the tangency order actually says? It says that if I pull back the equation defining the ith divisor component, then there should be a monomial in the equations defining the markings, okay, equals 1 to n, of spj with the appropriate exponents, so alpha and j. Okay, and this is for all I. So let's just think about what's going on here. So, okay, so this is a section of the line bundle of di, which vanishes along di. This is a section of the line bundle, the appropriate sum of the markings on the curve. And so what I'm really saying here is there should be an isomorphism of those line bundles which identifies these sections. And that's precisely saying that this map vanishes. Okay. So this is sort of, you could consider this space that I've written down. I mean, this is perfectly fine. Unfortunately, the space won't be compact because what could happen as you look at limits of families is that, for example, this could become zero, identically zero, because your curve falls into divisors. And so there exists a compactification, which is the state of log maps. Okay, and I'm not going to go into the details about what this looks like. Just take it from me. So there exists some compactification, and the compactification is important because we want to integrate over this. Okay, so as with the space of ordinary maps, okay, these spaces of log maps are arbitrarily singular. Okay, so they also satisfy this theorem back here. But there is a crucial difference. So over here, I told you that kind of everything was terrible, but actually everything was fine. But in this situation, sort of everything is terrible, but everything is not quite fine. Okay, so unlike, this is somehow a crucial difference, is that unlike these spaces of ordinary stable maps, these spaces of log stable maps are not quite smooth. Oh, sorry, they're not quite virtually smooth. They're only virtually irreducible. Sorry, they're only virtually irreducible. And the culprit is actually tropical geometry, and I'll explain why by the end of this talk. Okay, so let me explain what I mean by this. So I said that something being virtually smooth is basically saying that I understand the deformation theory of this thing, okay, which is saying that this thing with a perfect obstruction theory exists. For log stable maps, we don't quite have this thing with perfect obstruction theory. So what we do have, so we have a perfect obstruction theory relative, basically, let's say over some smaller space, which is something called the space of log maps, the Artin plan, which is the universal target. Okay, so let me explain what this is. So in the same way as over here, I have a map of pairs. This is also a map of pairs, but this is some slightly kooky object. Okay, so what A is it's a global quotient stack. So it's the quotient of A1 on GM. Okay, and a map to A from any scheme is just the data of a line bundle on that scheme and a section of that line bundle. Okay. In some sense, this follows formally from the definition of a quotient stack, but it also sort of just makes sense if you think about it, because you know, giving that to A1, right, is just giving a function on your scheme. Okay, so if I have a section of a line bundle, then locally that is a function, right? It's just that it doesn't glue together sort of in the obvious way, because somehow on the overlaps there's a GM, which is somehow telling me how to transition from one chart of my line bundle to the other chart of my line bundle. So if I mod out by that GM on the target, then I have a sort of canonical map to A1 mod GM that does just glue kind of across the whole scheme. Okay, so this is somehow the moduli space of line bundles with sections. And I'm going to claim that there's somehow a forgetful map here. Okay, so I should take a map to X row D and just remember n line bundles and n sections. And which line bundles and sections am I going to remember? It's going to be these ones. Okay, so maybe I should. Yeah, my board work is not great this evening. I'm sorry about this. So let's write this out again. That wasn't deliberate, but I guess it worked out okay. So if I start with some map, okay, and then yeah, fine, I also have these markings. So what I'm going to do is I'm going to retain the source code. So the source code is still going to be there, the markings are still going to be there. But I'm going to forget the map, and I'm just going to remember the bit that's relevant to the divisor. Okay, so I'm going to remember n of these pairs. So it looks like F star O of D1 together with the fallback. So that's D1, blah blah blah, down to F star n. So this is something called the universal target. The idea is that somehow every S and C pair with n elements will sort of pull back from this one. So if you can solve the problem here, then you sort of solve the problem everywhere.
So it's not the Artin plan of X.
It actually is, well, it's more or less the Artin plan of X. So it depends on. So let's assume.
It looks like there would be only like a single closed stratum or something.
Sorry.
Because it's only a single column, right?
No, so this is A to the n relative to the boundary. I guess I didn't tell you what the boundary is.
Oh, okay.
Yeah. So but maybe now you see what it is. So it's, you know, each of these factors has a divisor, and I take like that divisor times everything. I just pull it back from the factor to here, and I take the sum. So this is actually a union of n divisors. Here.
I see.
Yeah.
Okay.
So this is, I mean, let me answer your question. So this is the Artin plan. So let's assume, okay, and you don't really lose much by doing this. So if we assume that the tropicalization of X row D is actually equal to Rn plus, this basically means we're assuming that all of these divisors like intersect like actually intersect. They don't have like empty intersection, right? So like every subset of these devices has empty, not connected, non-empty intersection. Then in that case, this actually gives the Artin fan of the pair XT. And otherwise, this is just going to be some sort of like subcomplex of this, and then the Artin fan will be an open of this, so you don't really lose much by passing this thing. Yeah, thank you. So we have this forgetful map, and this map has an obstruction theory. Okay, so in other words, if I give you, if I think about the problem of choosing some element here and choosing a lift, this is something whose deformation theory we do understand. Okay, and so we sort of got half of the way, but the problem is we can't go all the way down. So the problem somehow lies here. Okay, so this space, the log maps to the Artin fan. This is irreducible, but it's not smooth in general. And so consequently, the space of log-stable maps is virtually irreducible, but not virtually smooth. Okay. And so because of this, so some things are okay. Okay, so because it's irreducible, it has a fundamental class. And then the fact that somehow this map is in some virtual sense smooth allows us to define a virtual fundamental class here. Okay, so we get a virtual fundamental class on this space of log maps. And that's important because we can define invariants. Okay, so we get these log Gromov-Witten invariants. Okay, but a lot of these other, well, I didn't really use this space very well. So a lot of these other techniques which exist, like torus localization and various other things, they no longer work, okay? Because for them, you really need to understand all the deformations. It's not enough to understand the deformations over sometimes they reduce, okay? So we have these invariants, but they're harder to compute because we have fewer techniques. Okay, so our goal for today, is to understand the singularities of this space. Okay. And the idea being that if we understand the singularities of this space, then in some sense we're understanding the virtual singularities of this space. Okay. So here's a fact, okay, and this really comes from sort of log deformation theory. Okay, so the fact is that this space is actually itself a toroidal embedding. Roughly speaking, it's a log smooth log stack. So this is a toroidal embedding. I mean, it's an Artin stack, okay, but it's as close to being a toroidal embedding as an Artin stack could ever be. Okay. And so what that means, of course, is that its singularities are at worst toric. Okay. So now I can state the theorem. Going until 5:45, right?
Yeah.
Yeah, okay, great. I didn't remember when we started. Okay. So we have this thing, it's a toroidal embedding, which means that locally it's the toroid variety. So the singularities are worse for it. So the theorem. Probably guessed by now, is that actually all toric singularities appear. Okay. So let's say that precisely, yeah. So for every toric singularity, there exists some n such that the singularity is in some space of log maps to the Artin type. Okay. So this is a, if you like, this is a virtual toric Murphy's law for spaces of log maps. Okay, let's get back to tropical geometry. So how are we going to prove this result? Right. So I told you this thing is a toroidal embedding. Okay. I should have told you what the boundary is, right? So a toroidal embedding is really a pair. It should be a space together with a divisor. Let me tell you what the divisor is. So the boundary is where the curve breaks. Okay. So here's an example. So let's say this is our divisor, D, and let's say our curve breaks into sort of 3 pieces, something like this. So 2 of them, C1 and C2, are sort of mapped out of the divisor, and they have some tangency here, where they meet the divisor, and then there's an internal component which is mapped entirely inside the divisor. So this would define a moduli point in this space of log maps, and that would be considered to be inside the boundary. Okay, so it's basically where the curve is not smooth. Given this picture, we can kind of draw a dual picture, okay, which is going to be tropical. So in the dual picture, what happens is my divisor is represented by a ray, okay, and the rest of x is represented by this vertex here, and I'm going to draw my source curve above, okay. So I take the dual graph of my curve. So let's say this is C1 and this is C2, and I'm mapping these to x minus d because C1 and C2 are mapping to x minus d geometrically. And then I have C0, right? And that's mapping to d because C0 is mapping to d. Okay? So we have the geometric picture over here, we have the tropical picture over here. Okay? And what you'll notice is that this is precisely what I call, and then there's some numbers here, right? So these expansion factors, and these are going to correspond to the tangency orders here, okay, at these nodes. So let's say this has tangency, I don't know, 4 and 5. And these expansion numbers would be 4 and 5. Okay. So what we see is that this picture that I've drawn, which is just modeling, basically just extracting the kind of strata data of this algebra geometric picture over here. This is what we call a tropical type at the beginning of the talk. Okay. And so the observation is that boundary strata in this space, okay, so in this space that we want to study. Okay, so this set of boundary strata is sort of in bijection with this set of tropical types of maps to Rn. Okay, but actually more is true, right? So if I look at a boundary stratum here, then there's a local toric model, okay. And that toric model is going to be the toric variety associated to the tropical moduli space that we looked at the beginning. This cone, this rational polyhedral cone that was associated to a tropical type. Okay, so the local toric model, I guess, let's say at the generic point of a stratum. Okay, so this is just an affine toric variety, right? But possibly singular. Is going to be equal to the affine toric variety associated to this this thing that I called the tropical moduli space, which was just a single cone associated to a given type. And therefore, as a result of this theorem, as it's on over here, so the main theorem reduces to the following combinatorial theorem. Okay, so now you can maybe start to see why this was an undergraduate project. Okay, so the theorem says that every, what's the right way to say this? Yeah, so that for every, strictly convex rational polyhedral cone sigma, there exists an n, oops, n in Jesus Christ, okay, so n in n, such that and a tropical type mapped to Rn positive such that the moduli space associated with this tropical type is isomorphic to sigma. Okay, such that the moduli space is isomorphic to sigma. Okay, so now it just somehow reduces to answering this combinatorial question. Okay, great. So this somehow combinatorial theorem, given somehow these facts that I told you here, implies the algebra geometric theorem. Questions? Oops. So if you've forgotten how this tropical moduli space is constructed, that's okay. I'm going to do an example now, and hopefully that will jog your memory. So I'm going to run through this theorem in an example, but the example more or less, with enough bells and whistles, kind of contains the whole proof. Okay. Oh, I didn't do that. Okay, so we fix our sigma, right? We fix our sigma, and for various reasons, we actually find it easier to work on the dual side. Okay, so we set let P be basically the semigroup of the points of the dual axis, right? So sigma is some cone living in NR. P is this monoid that we use to construct the affine toric variety. So here's an example of what P could look like. Let's suppose P is given the following presentation. So N4, and then I'm going to mod out by some relations. So E1 plus, E2 is 2E3 plus E4, and by E1. It could happen. So what have we got to do, right? So we've got to construct a tropical type, so there's data of a graph and so on, whose associated moduli space will give me this monoid, okay, or the corresponding code. So here's what we do. We notice something, okay? So we notice that in these relations, E1 and E2 are only appearing on the left-hand side, and E3 and E4 are only appearing on the right-hand side. Okay? So we draw some picture. It's going to look like this. Okay, so this is going to be our graph gamma. Okay, and the idea is that you have a sort of root vertex, and then you have two paths, and the paths are going to be indexed by the left-hand side of these relations and the right-hand side of this relation, or the generators. Sorry. So E1 and E2, these are kind of my generators which appear on the left-hand side, and E3 and E4, these are kind of my generators that appear on the right-hand side. Okay, so that's for the generators. So what about the relations? So we need to force these relations, and remember, I said that for every cone there exists some n, okay? So I get to choose n in this case, and what I'm going to do is I'm going to take n to be the number of relations, okay, which in this case is 2, okay? So I'm in some two-dimensional space, so I have two-dimensional slope vectors, and what they're going to do, maybe I'll write them down, and then you can see if anyone can spot the pattern. So in this case, they're 1, 5, 1, 0, 2, 0, 1, 1. So they're coefficients, right, that the generator appears in. And so somehow each dimension is corresponding, like, this row is corresponding to the first equation, this is corresponding to the second. Okay. So now I specify the data, let's draw it more geometrically. Okay, so I have my target, and then I'm going to draw the curve now. And so what I'm going to do is I'm going to force these two to map to the origin. Okay, so these are both forced to map to the origin. I'm allowed to do that because I'm mapping to a cone. And now I have to put in these vectors. So let's see if I can do this live. So let's say this is D1 and this is D2. So 1, 5, yeah, should be like this. 5, 1, 0 should be like this. It's a bit longer. And then, yeah, something like this. 2, yeah, 2, 0, and 1, 1, and they meet at this point, B0. Okay. So it looks as if the curve has genus 1, right? But that's just because I map these two vertices to the, and the image has genus 1, but the source has genus 0. So that's fine. And then, okay, so these edges all have lengths of the source, right? So E1, E2, E3, and E4. And now what we do is we basically say, okay, if I start here, I can either go sort of this way to get to D0, or I can go this way, and I better end up at the same place at the end. Okay. And so there's somehow two relations. So the x direction, right, is going to give me, if I go this way, then it's E1 plus E2. Right, those are these two things here. Whereas the y direction, whereas if I go this way around, it's just 2E3 plus E4. And these two things have to be the same. And then the y direction is similar, right? So if I go this way, it's 5E1. And if I go this way, it's E4. Okay, so lo and behold, I recover the relation that I was on. Okay, so so I have about 5 minutes. So okay, so in general, I mean, I don't need to write this, but you know, basically what you do is you start with some monoid, and you give it some, you know, you express it, you give it some presentations, you express it as some quotient generators with relations, and then what you do is you take this presentation and you perform some surgery on it. So you replace it by a presentation, something that we call bipartites. And what this basically means is that the generating set kind of decomposes in this way, okay, into a disjoint union in which elements of this thing only appear on the left-hand side of relations, and elements of this thing only appear on the right-hand side of relations. And actually, it just so happens that actually for every monoid, you can always start with a given presentation and construct a new presentation that has this property. Okay, it might be very redundant. You might need a lot of generators, but nevertheless, you can do this. Okay, and then the proof basically runs exactly the same. So the curve will reflect the structure of these generators, and the dimension of the target will be the number of relations. Okay. And okay, again, for the experts in the audience, there's lots of subtleties involving integralizations and saturations of monoids and various other things, but you know, don't worry, we thought about that, and it all turns out to be fine. So I'll just end with a question. Okay, so this result says that all toric singularities appear, but notice, right, the dimension you have to go to depends on the singularity that you started with, or at least the way that we stated the theorem it does. Okay, so here's a question: does there exist some uniform n? Right? So certainly, in our construction, n can be essentially unbounded because you can always find monoids that require sort of arbitrarily many relations to present. Okay, so this n could grow very, very large as the singularities become very, very complicated. Okay, but of course, our construction is only one construction. There might be other constructions that are more efficient. Okay, so we don't know the answer to this. We don't know if there exists a uniform n. But what we are able to show is that n equals 1 doesn't work. Okay. Okay, so it turns out that if you take the cone over the k-gon for k at least 7, then this never appears in the space of tropical maps to R positive or n equals 1. Okay, so in other words, yeah, for n equals 1, this modulo space does not have arbitrary stroke singularities. These stroke singularities don't appear. Okay. But you know, sometimes I think as Luca pointed out to me, sometimes once you go to n equals 2 or n equals 3, you sort of have enough freedom to to get everything. So we don't actually know whether, for example, once you get to n equals 2, it might be enough, and you might be able to get all the singularities. So anyway, I'll stop there. And yeah, thank you.